Now we learned in class that there are planes that exist in a crystal, and these are useful when thinking about certain properties in crystals. So things like anisotropic behavior. It requires that we are able to unambiguously describe direction in a crystal, to describe the distribution of atoms along certain preferential directions. Now, one of the ways this is done is by using the idea of Miller indices. And what they help us to do is to describe the orientation of a lattice plane and be able to compare it to the reciprocal lattice vector, or really to have a one-to-one correspondence with the reciprocal lattice vectors. So the way you would describe a plane mathematically is by using what we call the vector normal to the plane. So that is how you describe a plane. You take a normal to the plane and use that as a reference, indicating where the plane normal is pointing towards. Now, we already described this, so let's see a worked example of how you would move from a plane to the Miller indices of the plane. So how does this work? Now, the first step, of course, is to consider the intercepts. So the first thing we do, now in the first example, we have a plane. So this is a plane that's facing the x direction, and it intercepts at the lattice points, and we know this is a lattice vector A, or we simply call it the unit length. So it will intercept in the x direction at A, it will not intercept the y direction, and it will not intercept the z direction. So we have x equal 1, y and z equal being infinity. So these are our intercepts, 1, infinity, infinity. If we take the ratio with the unit length of each vector, of each unit vector in each direction of x, y, and z, we have a being 1, b equal 1, c equal 1 in magnitude. So we have 1 over 1, infinity of 1, infinity over 1. If we take the reciprocal of this, we end up with 1, 1 over infinity, 1 over infinity. So the last two quantities here rapidly approach 0. And we end up with the Miller indices 1, 0, 0. In curly braces. So we always use curly braces to describe the Miller indices. Now, on the other hand, let's see a different example where we have an intercept at A in the x, an intercept at A in the y, and no intercept at z. So how does this look like? We end up with the intercepts of 1, 1, infinity, a ratio of 1, 1, infinity again, and a reciprocal of 1, 1, 0. And this then becomes our Miller indices. As part of today's tutorial, I will require you to work out these three examples that are also in your on the Moodle platform. So work them out, find the Miller indices, and upload the answers within 2 hours of the end of the lecture. So this is an exercise that are required to be returned before the end of the lecture. You'll be required either to upload the answer or to fill it in your text box. So that will be the end of today's tutorial.